Earth science time. Today we're talking about, let's call it specific erosional media. Specific erosional media. And I would love to get through all of them today. They're going to be kind of surface level, obviously, because there are quite a few of them. We're going to get in more depth than we did last time. But if we don't get through all of them, we'll have a part 2. We'll just see. Qu'est-ce qui se passe, right? We were just talking about French, weren't we, Camden? So we already know all of our French. Okay, so we do know about erosion and deposition in general, right? And we know about weathering in general, right? Would someone just remind me real quick, what are weathering, erosion, and deposition? Weathering is the breakdown of rock.
And erosion is the movement of the sediments.
Erosion is the movement of sediments.
And the deposition is the dropping of the
material. Yeah, deposition is the dropping of the material. Good. I like those definitions. Fine. So the first, and we had several different kinds of erosional media. What were the kinds of erosional media? I want to hear their fancy names. The fancy names, yeah. Yeah, we're not going to start with aeolian, but aeolian is one of them. In fact, let's write it down. We'll have aeolian. Fluvial, that is the first one we're going to talk about. Marine. Lacustrine, and we'll put that in with fluvio.
And glacial.
And then glacial.
And then biogenic. And then we have mass movement.
And let me see if your book talks specifically about mass movement. I will still list it because put it under here so that we can still see it on the camera. Mass movement.
Biogenic, which is when life.
And then biogenic I'll put over here. Bio. No, it's not out of sight. We can still see it. I just want to see which of those. Your book specifically talks about fluvial and lacustrine. It talks about marine. It talks about glacial. And it talks about aeolian. So those are the ones we'll focus on. We'll touch briefly on, let's do mass movements in biogenic first. I just want to do a couple of things real briefly. We'll probably, for each of these, we'll describe it, and there might be some more details that need to be elucidated, and then we'll provide an example. We'll try to do that for all of them. So let's start with biogenic. As we said, that biogenic means what is producing the erosion, or what is producing the weathering, or what is producing the deposition. What?
Life.
Yeah, life, not just humans. In fact, probably mostly it is humans. I don't know, maybe not mostly by like amount of it done. Human beings do a lot of biogenic erosion. Anytime sediment's transported, it is erosion. And so even if, like, by transporting sediment, I mean I have a hole in my driveway that I need to fill in with dirt, my transporting that sediment, what? No, that's a different thing. That's not me. But the sediment being transported by me in a shovel, that's still biogenic erosion. So that's life. But then what are some other things that are non-human? Remember, we do count human activity, but what are some things that are non-human that would count as biogenic erosion, do you reckon? I can think of one really major one that you can probably think of pretty soon too. It doesn't have to be animals, because that's what, and the animals do it, you know, like a badger digging a little hole to plop out its little puppies. That is biogenic erosion. Yeah, what kind of, well, yeah, what do plants do to the sediment around them?
What I was thinking,
How?
if a tree, like if it was growing like big trees, there are roots.
Yeah, roots. Usually, I would say root activity is actually probably, that's what, when I first started saying human beings are the major contributors to biogenic erosion, and I kind of stopped myself, it's because I think probably roots of plants is a much more major source of biogenic erosion. Do you have questions about biogenic? Any questions that you have, this will probably be cursory, like define biogenic erosion, for instance. Do you have questions about it, though? Okay, let's move on to mass movement. Mass movement is separated by its speed, and we call them, we have different speeds of mass movement. Creep, slump, slide, and fall. And these are in order of increasing speed. Creep is like, and this happens a lot more in environments that have wetter soil or bedrock than here. And so sometimes you will find, and the classic example of this in the hills on the East Coast and in the southern United States that have like graveyards on them, very old ones will often have the tombstones will all be pointed downhill because over time the sediment has slowly moved with the bodies, with the vegetation, with the gravestones. All of that has slowly moved downhill, and that's creep. Slump is when a large part of land kind of falls at once, and a lot of times it'll make a crescent-shaped scar. So there'll be a hill, and then a part of the hill will kind of cave away, and they'll leave this like crescent-shaped area, not underneath it. I'm looking at the hill, not a cross-section. And it'll leave this crescent-shaped scar, and that is, and it's not, it can happen fairly quickly, but it all is still, like, you know, it's not a fast thing. Whereas a slide is like a landslide, you know, like the Stevie Nicks song. That's where rocks are sliding down a hill, and they end up in a little pile at the bottom. Yeah, that's the one. Yep. And the only difference between these two, the last two, slide and fall, can both be very fast. But in a fall, for at least part of it, the rocks have to not be touching anything else. So these both happen fast. But in a fall, at one point the rocks are only in free fall. That would be a rock fall. And in a slide, they're in contact with other material all the time. It's just a fast movement. Do these kind of make sense? And what is the driving energy source for these? Gravity. Yeah, these are all driven by gravity. In fact, this, and this, these three, I'd get them alternating. I would say these three, biogenic, aeolian, and marine, are more or less solar driven. And then mass movement, fluvial, and glacial are more or less gravity. And there's a combination of solar and gravity in each. Why am I selecting solar and gravity? What is so important about those two energy sources? Yeah, they're the most basic energy sources. Like if we think about, for instance, biogenic erosion. What the energy source for me hauling a shovel full of sand, my energy source for that, well, first of all, it's my muscles. And then the energy that they have came from my Subway sandwich. And the energy and all the ingredients in the Subway sandwich, eventually, if we go back far enough, came from the sun. Solar. Aeolian is powered by what? And we'll talk about this one next. What is the unfancy name for this?
Isn't it wind?
Wind, yeah. And the reason that wind is actually solar power is because all wind is a fluid flowing from a high pressure to a low pressure. Just like if you have a water bottle, like a plastic water bottle, and you squeeze it. I did this in the Bernoulli's principle, or the Pascal's principle physical science video here recently. I had a plastic water bottle I stole from Peyton Moreva, grabbed it, took the lid off, and just went like this. And I applied a pressure inward to the fluid, right? A high pressure, and the water came out the top to a low pressure, the environment. All wind is a flow of air from relative high pressure to relative low pressure. And what causes the pressure gradient? What causes the pressure differential on planet Earth's surface? Do you think? Like, why would one area, look at the flag, I can see that the air is moving from the north to the south. Why would there be lower pressure somewhere south of here than north of here? It doesn't always move that direction, but in this particular case, what's different? What has caused that pressure gradient, do you reckon? Gravity? Probably not. There's probably not more gravity south of here. Something in the atmosphere, though. The different amounts of what? Solar heating is what it is. It's solar. This is powered by the sun. So life at its base is powered by the sun. Mass movements are powered by gravity. This would keep happening. If the sun blinked out and everything else was dying, there would be no more biogenic erosion. There would still be mass movement. There'd probably be no more wind because it's driven by the sun. But there would still be, and we'll come back to Aeolian in a second to talk about the features, there would still be fluvial, right, for a while at least, until everything froze. And even then, we'll talk about glacier in a second. But until everything froze, the rivers would still flow. So then what is fluvial powered by primarily? What energy source is that? Well, yeah, but there's only two main energy sources. No, not the sun.
So is it?
Gravity, yeah. Gravity is what's causing a river to flow downhill. I will say that the steeper a slope, the faster a river flows. And then kind of a corollary to that is that wide rivers form on flat-ish plains. Well, why might that be? Why don't we have big, wide rivers on very steep slopes? What would we find? Do we have a whole lot of very fast-flowing rivers around here? Not very fast, no. Where would we go to find very fast-flowing rivers? The Amazon doesn't flow particularly fast. It's quick. But where would we find the fastest streams? Where would we find the fastest? I'll go back to mass movements for a second. Where do we find the fastest movement of sediments? Yeah, when the thing is water. Steeper. Yeah, we find faster moving fluids when it's steeper. But also, think about it this way. If we have this mountain here, and here's our source of water, probably a snow cap, and it's flowing down, as it flows, it's going to do what into the sediment around it? The river will do what to the sediment around it? Or these rivulets? Yeah, it'll erode it. It'll do what we call down cutting. It's all one word, but I ran out of room. And it down cuts, which means it cuts down into the sediment until it's at the same level as where it's going to end up. So it'll end up down here on this plane. But by then, because these rivulets, because these rills and gullies have been cut down into the channel, these channels are already narrow. And all the water that flows through them is a relatively small amount of water, but it's moving pretty quickly because it's steep. And then by the time it gets down here, eventually these might recombine, and this will have a larger volume of water, but it'll probably be moving slower. I'm trying to draw it like, this is supposed to be three-dimensional. Give me a break. It'll have a larger volume of water as it moves on, but it'll be moving quite a bit slower. So what size of sediments are probably moved up here? Probably small pebbles. Maybe if it's very fast, there might be some waterfalls that a large pebble might fall down.
Like dirt.
Dirt's not really a size of sediment. Sand is probably moved. So all of the clay and silt and sand that are present up here get washed away. And what's left is pebbles and larger. So we have what we think, when you think of a mountain stream, you think of nice crystal clear water with pebbles on the bottom. You know, you think of a bear fishing salmon in the river, it's probably pebbles on the bottom. That's because it's moving fast. And that's also why it's clean. It's coming from ice caps, which there's probably some dirt and leaf litter and stuff in there. But as it moves along, all that stuff gets transported downhill very, very quickly. And then down here, the sediment has probably all come out. And so we've got sediment deposits here, deposition. Then we've probably got silt deposits here. And then what's carried on by the river is just clay. That's why the Mississippi River or the Amazon River, if you look at pictures of them, what color do they look like? Like if you're a child, you draw them as blue. But if you actually saw a picture of the Mississippi River or the Amazon River, it looks brown because it's carrying silt. It's muddy. Yeah, there's just muddy, silty water being carried along. And then where is that deposited? Where does that get deposited? So we had sand deposited here. The pebbles are deposited up here, right? Sand's deposited here. The silt gets deposited in this floodplain down here, which is why places like this are very fertile, because there's silt deposits all over the place. Sand, pebbles. Do you see the correlation between size of sediment and steepness of the area? And then where's the clay get deposited? Well, conveniently, right here in the marine. Deposited in a delta. We call this area here a delta. And if we take a cross section of the delta, we will see usually we'll see a sequence of sediments that is what we call fining upward. So we'll have the coarsest sediments on the bottom, then slightly finer, then finer still, and then the finest sediments on top. And that's because what gets deposited the farthest away from a delta? Imagine we had a very fast-flowing river and all these things were still in the river when it went into the delta. What gets deposited first? Like what will stay closest to the mouth of the delta? We saw this in the lab too. What will be deposited out first? Which of these things, pebble, sand, silt, or clay, will fall out first? As it slows down, as it goes into another slower body of water, the first thing to be deposited will be the pebbles. The pebbles will fall out first, and so those get deposited on the bottom, or really they get deposited closest. And then the sand, silt, and clay. And so really this is kind of a sequence sideways. So the pebbles get deposited first, and then the sand, and then the silt. Do you see these little symbols that I'm making here? Have you seen these before? Have we talked about those? Okay, let's talk about those real quick because it does come up quite a bit. I'm trying to make them better than this. We use these symbols to represent the different sizes of sediment. Circles we use to represent pebbles. Dots are sand. And then a dash and then a dot, like an alternating dash, dot, dash, dot, dash, dot is silt. And then we use dashes for clay. And then as this becomes the land, now the pebbles get deposited on top. The sand gets deposited on top of this one, and the silt gets deposited on top of the clay. And so really, I think I had lied to you a second ago. What the sequence we actually see in a deltaic deposit ends up being, ends up being one of coarsening upwards. Coarsening upwards. I think I might have lied to you. Did I say fining upwards a second ago? It should be coarsening upwards. It should be finest on the bottom and coarser on top. Because as this becomes land, the delta moves out farther, and finer and finer and finer sediments get further away, but then the coarser sediments get deposited on top. That's one kind of marine feature. Another kind, and I really like these, if you look at, there's a diagram. Oh, did you bring your books with you by chance? No. I wish you did. But you did the explorations, some of you. Did you do your explorations, Kyla? It's okay. You don't have to be on film saying whether you did or did not do them. But I'm trying to think of how I can show this to you. Well, we'll look at this when you do, after the video, we'll look at this on your explorations. But for now, let's look at the erosional media, or the erosional features. This is a depositional feature. How can I tell the difference in general between a depositional feature and an erosional feature? Not by appearance, but what's the main difference? Depositional features are formed through what process? It's in the name. No. Yeah, depositing. Depositional features are formed when sediment is deposited. Like this sequence of sediments here is formed when deposited by a delta, whereas erosional features are formed by erosion, by removal of sediment. So the valley left behind up here in the mountains would be an erosional feature. A little ripple of sand down here would be a depositional feature. Anyway, some of the erosional features of marine sediments are really cool. There are things like sea stacks and sea pillars or sea arches, which is where there's an existing cliffside or something next to the sea, and then as waves continually crash into a small crack, the crack gets bigger. So this would have started out as just a cliffside, and there would have been a crack, and the crack gets bigger and bigger and bigger and wider until eventually it's either a sea cave, or if it's disconnected from land, it becomes an arch, or if crack gets big enough and it separates this into two things, then it becomes a sea stack. So this is a stack. This is an arch. And then a sea cave can form in the same way. But basically in all of those, it's a crack or something, some abnormality in the surface that as the waves crash into it over and over and over again, it gets bigger and bigger. And there are two other things that I want to talk about in marine, but I really kind of would like to show you the pictures from the explorations in order to talk about them. Let's now talk about glacial erosion.
Wait, what is marine caused by? Because like
Oh,
solar gravity.
yeah. What do you think?
Would that be?
It kind of depends. It's kind of both. This would be gravity, mostly. The depositional feature that we talked about, the deltas, because they're really kind of a fluvial feature. But most, like the tides and the currents in the ocean are caused by solar. So it depends on which part of marine erosion we're talking about in marine deposition, but the ones that are caused by the ocean itself, by the waves crashing and by the currents in the ocean, that's caused by solar energy. What's a glacier? You have other questions about any of this? I haven't done a good job asking you. Do you have questions, Kyla? Okay. What's a glacier?
Ice.
Ice? Yep, it's made of ice.
It's just a bunch of ice compacted into a big solid of ice.
Yep, big solid of ice. And there are two kinds of glaciers, really. We talk about, I'm trying to draw a glacier up here. If it's within the mountains, like if there are mountains around, and it exists because of altitude, we call that a alpine glacier. But if it exists because of, we could think of like the Arctic Ocean today as a giant glacier. And that exists not because of altitude, but because of latitude. Like it's because it's nearer Earth's poles. But if it takes over a whole huge area of land, we call that a continental glacier. This one's an alpine glacier. But a continental glacier forms over a large area of land due to continual low temperatures. And a glacier starts to form when there's snowfall, and then before that snowfall melts, there's more snowfall, and then there's more snowfall, and it keeps piling up over and over and over again. And as it compacts, it's not that we tend to think of ice, if it's just pure ice, that it must have been a liquid one time, but usually it's just compacted snow. And it's solid ice now, not because it ever melted and then refroze, but because it has been pressed down. And glaciers move. I think it's interesting how glaciers move, which is that there's so much pressure because of the enormous weight of ice that the bottom part of the water actually melts. Not because of a high temperature, but because there's so much pressure that can't exist as a solid. And that is how a glacier is able to slide. So the ice itself is sliding on a thin layer of water. And then that's driven by, of course, what major source of energy? Gravity. Glaciers we associate with poorly sorted, even very poorly sorted sediment. From anywhere from boulder size to clay size. It doesn't happen in here at all because there haven't been, since the entire Earth was ice during Snowball Earth 600 million years ago, there has not been a glacier here. And so we don't really see this. But if you go to a place like the Great Lakes or Canada, there will just be boulders sitting in the field. And it's because they're ancient boulders that are just sitting there from when glaciers had carried them and dropped them off in that area. But they're poorly sorted, and that means, you remember talking about poorly sorted back when we did the first unit like 2 months ago about erosion and deposition. It's considered well sorted if it's all sand sized, for instance, or all pebbles. Doesn't matter what size it is, but if all the sediments are the same size, that's well sorted. But glaciers exhibit poorly sorted sediment. Like there'll be a boulder, and then right next to it will be a tiny little rock, and then there'll be some sand, and it's just all mixed together. And as a glacier moves forward, it moves this big mess of sediment, this poorly sorted mess of sediment in front of it. So this is the glacier, or it's supposed to be the glacier, and then this is the poorly sorted. Here's a boulder. There's some gravel in it. Here's some sand. There's some silt and clay, all different sizes of sediment. And we call this a moraine. And then what happens is the glacier, as it starts to retreat, which glaciers usually do, some are periodic, they'll go forward in the wintertime and they'll come back in the summer because they melt and freeze, etc. But the moraine, this pile of sediment kind of gets left behind. And the glacier also digs out a U-shaped valley. U-shaped valley. And that's as opposed to, we're going to go back to this, but these valleys in the mountains here from fluvial erosion would form what shape, do you reckon? I've kind of drawn a few of them. V-shaped, exactly right. A V-shaped valley. The reason this one becomes V-shaped is so say we start with a flat area. There's a little river in it, and it gets deeper and deeper, and the river itself is pretty narrow, but then as it gets deeper, the sediments from the walls around it start to fall down too, and we end up with this V shape because every time it cuts down, the walls cave in. So that ends up with a V-shaped valley, and here we get a U-shaped valley because the glacier comes along and it's kind of like digging out a chunk, and then as the glacier melts, we left with this valley that has fairly steep walls, and that's a U-shaped valley. Let's list some very specific erosional features from each of these, some examples, and then we'll be done. Okay, do you have questions about kind of the processes? We already did list some examples. I told you moraines and U-shaped valleys for this, but do you have questions about the processes in general? Okay, let's start with the mass movement one then. We call one example of this an alluvial fan. Just like there's a area of sediment kind of at the bottom of a hill, and that's an alluvial fan, and that's because it's usually fan-shaped. A lot of times it'll form also, I should put this kind of in the middle, it is a type of mass movement, but it forms when a river flows out onto an open plain. And then obviously as the water spreads out, it can no longer, it's not moving fast enough to carry its sediment, so the sediment gets dumped. So this is water, and this fan that's formed, you see why it's called a fan? It's kind of shaped like the fans you used to make in elementary school with the corrugated paper. That's an alluvial fan, and that forms when water or a slide flows onto a plain. We associate this mostly with deserts because the deserts will be completely dry, then there'll be torrential rain, which will carry a lot of sediment, and it'll flow out onto a flat plain, and it'll just leave all that sediment in a fan-shaped pile there. And I put it kind of in between fluvial and mass movement because you can consider it part of both. Oops, it's supposed to be over here with fluvial. This is getting kind of messy. I made it messy. We call you good on alluvial fans? You good on alluvial fans? Okay. We call the artifacts, the things left behind by aeolian erosion, ventifacts, which comes from the Latin word for wind, which is ventus. We call them ventifacts, and there are things like dunes. You know about sand dunes. Most dunes, I'm drawing kind of a typical example of a classic dune. This is the direction of wind. The wind flows this way, and what happens is sand gets picked up and pushed overboard, and then it kind of leaves this gap here where the wind isn't blowing. We call this the windward side, and we call this the leeward side. There are also things formed by wind erosion called yardings, which are these like mushroom-shaped structures. I would be very impressed if you can, but can you guess why these would be mushroom-shaped like this? Maybe, Camden, maybe you read about it. We see these something roughly like this at Toadstool Park, just north of here. Have you been to Toadstool Park? The reason it's called Toadstool Park is because there are these things. People don't call them Yardings, and they're not quite the same thing. But can you guess why these are this shape, where they're kind of a little bit fatter on the bottom, and they get really quite thin, and then they're wide on top? What do you think? Well, let's think about how the sand's moving. Where's the sand probably moving the fastest? Do you think it's moving the fastest closest to ground? Nearer the ground is probably faster, but at the very, very closest to the ground, there's friction with the ground, so that slows it down. So it's moving at a certain speed here on the ground, but it can move a little bit faster as we go up because the wind doesn't have the friction, and the sediment that's already being carried by the wind that's knocking things loose can only get so high, and then it can't be carried any higher. So no matter how fast the wind goes, the sand can't go that high. Does that kind of make sense? And so then it really starts to taper off pretty quickly, and that matches the shape of these. So they're thinnest at the height which sand can get to the best. The best combination of less friction and sand being able to be carried produces that shape. Your book lists 4 different kinds of dunes, and it's important to know the different ones, but this is kind of the general way that these dunes form. The ones that I've drawn here are transverse dunes, where the windward side is quite a bit lower, not quite as steep as the leeward side. And your book mentions those. We talked about the artifact of fluvial, which is mostly V-shaped valleys. The marine, we had these two things are both artifacts of the erosion. When I say artifact, I mean like a physical thing that you can see and feel and touch that's a result of these processes. Does that make sense? So the process itself we described, and then these are the artifacts, the stack and the arch, the moraine. These are the basic ones. I would say this is about 60% of the ones that your book says, and we've covered the whole dang board. Do you have questions about any of these things? If I had been very well organized, I would have done this all, then this, etc. But I kind of mixed around. But do you have questions about this? Do you know what to do if you do have questions? Yeah, ask me. I was hoping you'd answer that way. There are a couple of labs that we're going to do for this. I don't think we'll have the quiz until next week, but the last time we tried to do a lab, it took us several months. So this is your information. Your lesson self-check is due tomorrow. And we'll probably do the lab tomorrow. Does that sound fair?
Yep.
Okay. Bye.